Taking a look at another word problem, classified ad revenue. The table below lists the newspaper revenue for the classified ads for selected years of 1975 through 2009. For part A, use the graphing calculator to fit cubic and quartic functions to the data. Let x represent the number of years since 1975. Using the r-squared value, determine which function is the best fit. Part B, using the function found in Part A, estimate the newspaper revenue from classified ads in 1988, 2002, and 2010. Again, looking at the years, when they say let the base year be 1975, that is why x is equal to 0. 1980 is 5 years later. 85 is 10 years. So if I'm looking for something in 1988, how many years is that past 1975? That is 13. If I'm looking for 2002, how many years is that past 1975? That is 27. And if I'm looking for 2010, that is 35 years past the base year of 1975. So when it comes to looking for part B, those are the x values that we're going to be substituting into the equation that we're going to find. Again, when you make sure you put in the data into L1 and L2, make sure they do match up. If they do not, you will get the wrong set of numbers. For this particular problem, we were told to compare the cubic and the quartic. I went ahead and added the quadratic also. It gives me an r-squared value of 0.69. The cubic gives me an r-squared value of 0.90. And the quartic gives me an r-squared value of 97. The one that has the best fit is the one that has the highest r-squared. So, plugging into the calculator, we get each one of these, making sure we get the r-squared value to compare. Once we have that comparison, we are going to go with the quartic regression. I went ahead and did the scatter plot and inserted the y equals into the graph, and this is a scatter plot. Notice that the data is hovering around the quartic graph, so it's not straying too far from that line. That's why it is 0.97. So the equation that we have here is y is equal to negative 1.884 x to the fourth plus 0.009964 x to the third minus 0.15503 x second plus 1.3009 x plus 1.7727. For us to determine part B, there's 3 parts to it. Again, 1988 is going to be when x is equal to 13. 2002, x is equal to 27. And 2010, x is equal to 35. If you plug each one of them into your calculators, you're going to get these 3 values. For 1988, I will get a y value of $8.9937 billion. For 2002, I will get a y value of $19.862 billion. And for 2010, it's going to be $1.8358 billion. That's how we can use regression analysis to predict the future on certain problems. The next problem, we want to focus on the exponential function. This problem talks about the older Americans in debt. The debt among older Americans have been exponentially increasing in recent years. The table below lists for selected years the average debt per household, where the primary head is age 55 or older. A says using graphing calculator to fit the data for an exponential, where x number of years since 2000. B, graph the function found in A. C, use the function determined to estimate the debt for 2014. And then D, in what years the average debt among older Americans exceeds to 140,000. So we're going to take a look at part A. Again, look at the data. X starting at 2000 is 0 going through 8. Then L2 lists the average debt per household. Do your exponential is the EXP reg. And that will give me the equation of y is equal to 3247.445 times 1.0923 raised to the x. What makes this exponential is the fact that the variable is actually located as an exponent. The equation that we found is going to help us to do part C. We want to estimate the debt for 2014, which is 14 years after the base year. So I'm going to plug in x to be 14. So I would have an outcome of a debt of $111,771. It looks like their data is rounded to the nearest thousandth, so we may want to go ahead and round this up to 112,000. In part D, it says, in what year is the average debt among older Americans expected to exceed $140,000? Now remember that Y represents the average debt per household, while primary head is age of 55 or older. So in this case, we want to let Y be 140,000. Since we have the chart listed in the upper right hand corner, we want to know when is the Y value going to jump above 140,000. If you can tell by looking between years 16 and 17, it jumps from 133,400 to 145,700. So during the 16th year, it jumps over the $140,000 mark. So we can say during the 16th year, which would be 2016, the average debt will exceed $140,000. For this next problem, we want to focus on the logarithmic function or the natural log function. And this problem says in an economics class, students were given a final exam at the end of the course. Then they were retested with the equivalent test at subsequent time intervals. Their scores after time X and months are listed in the table below. 1 is 1 month past, 2 months, 3 months, and so forth. Part A says use the graphing calculator to find the logarithmic function of a plus b ln of x, which is actually number 9 on your calc. They wanted to use the function to predict test scores after 8, 10, 24, and 36. And then after how long would it take for the test scores to fall below 82%. So again, in order to use your calculator to find the regression of this, we need to make sure we put the data into the calculator. I'll usually try to use L1 and L2 for my X and my Y. To find the regression, go to Stat Calc and hit number 9. And the equation that we're going to look for here is Y is equal to the A, 84.9435, plus the B of a negative 0.5413 natural log of X. So in part B, we're looking for when X is equal to 8, when X is equal to 10, when X is equal to 24, and when X is equal to 36. Plug in those values. So after 8 months, the score would be 83.8%. After 10 months, it goes to 83.7%. After 24 months, the score goes to 83.2%. And after 36 months, your score is going to be 83.0%. So the longer the time goes, the less people retain. Now in part C, it says after how long will the test scores fall below the 82%? Now remember that 82% is represented by y, and we have the equation 84.9435 minus 0.5413 natural log of x. So we're looking for when y is going to be less than 82%. Now take a look at the chart in the upper right hand corner. We would notice that in 230 months, the percentage is equal to 82%. So that means in 231 months, these scores will fall below 82%.